This is the week 5 of the neural-based consciousness, and this week we're going to cover eyes, RE visual systems, and consciousness. Okay, so just to start from the recap of the last week, first we covered the properties of visual input to the brain. And through the structure of our eyes, retina, and the rods and cones, and we also compared that with the octopus. So this is the structure of the eye, and then important structure of like fovea and the blind spot, as rods and the cones, and its density here. I was compared with the octopus. And then based on the anatomical structure of the retina, we tried to predict what the phenomenology of fovea and also periphery should be like. So do you remember, or so let's go with the fovea. So the fovea has the highest density of the cones, and cones here in the fovea has only 2 kinds of the receptor at the very specific, central vision, which doesn't have this blueness, receptive, responsive cones. So that predicts that we may be blue blind over there. And then with some adaptation experiments, we were able to experience that there is something strange or something special about the very center of the fovea with respect to the red, the yellow-blue complementarity of the after image. And then at the periphery, as the cone receptors density goes down, like here and also here, some of the philosophers and also physiologists has been predicting or claiming that we should not experience color at all. And this is the version of the demonstration that I made for the class, and I'll go over it again. But I hope that you didn't, you sort of confirmed or disconfirmed their prediction so far. And then next was this properties of the visual input to the brain, and using this illusion or demonstration called a lilac chaser, I showed that the case where what we see is not what is there, and this is most eloquently sort of developed as a sort of theory called interface theory of the consciousness by Donald Hoffman here, and he says that the veridical representation of the outer world, meaning that consciousness as a sort of mirror replica of the outside world cannot be true, really true. And he makes this kind of argument through the evolutionary argument, but also he also talks about the quantum mechanics and the quantum information, and also various physics and some perception. And it's a very interesting kind of book. It can be a bit difficult, but I recommend for those who are interested in it. But the point here is that this type of the illusion, where if you fixate here, you hopefully see that only you see on the display is that the green thing that is moving, and you don't even see pink at all. So whereas what is there on the display is always on the a pink thing. So what you see is only green, nothing else, but pink is the only thing that is on the screen. So far, fine. And so here I also explained, gave a brief explanation of this lilac chaser coming partly from after image. And I'm going to explain what the after image means. But here, the complementary color of the pink is a green, and that's called after image. And I'll explain some theories behind it, and also go into the detail of what it means or what it has an implication for the consciousness, theories of consciousness. All right. So learning objectives for week 5 is that after week 5 lecture, you will be able to think and answer about the following questions. One is that what neural mechanism can explain the lower density of cones and vivid color experience at the periphery at the same time. And second is that what are the hierarchical structure of the visual system? And then third one is that which neural mechanisms are involved in after images. All right, so the first, so up to here was the recap. Is there any questions so far? It's fine. All right, then let's go. So the first part, how can we reconcile low cone density and vivid color experience at the periphery based on the architecture and the mechanism in the visual system? So our naive visual phenomenology makes sense in the sense that you probably saw color in the periphery, despite the fact that many prominent philosophers and psychologists claim that it can't be the case. And there is this intention. Why those people, famous people, make this kind of statements, and their statement is based on the physiological fact that the cone density declines as you go into the periphery. So our introspection or conscious feeling cannot be correct, and there may be some kind of feeling in based on the memory or expectation is explaining the phenomenology. However, that cannot be also the case based on the experiment that I showed last week. So let's go into the detail. And the key to understand this tension between this naive experience, but which is correct, versus physiology-based prediction, which is wrong, is that the concept of the receptive field in neuroscience. So the receptive field of the neurons in the periphery are, in general, much bigger than the receptive fields for those in the fovea. And that's one key aspect. So just to recap what I showed last week. So here's the areal color similarity task where we showed the 2 colors at the periphery from the fovea, and then 2 at a time each time, and then very briefly, like 250 milliseconds. After that, subjects press the button to say how similar or dissimilar each color is. And then based on this report, we try to carefully characterize what is sort of the structure of the experience in the fovea and also at the periphery. Okay. And then stimulus locations were random and also durations were short. So that means that we can't expect or memorize the color, and also we cannot make an eye movements to one area and then look at the other. And that's sort of dictated by the fact that the eye movement takes some time, like 150 milliseconds. So if you try to move your eyes, you can't do that within this duration, 250 milliseconds. And also, eye movements will blur the vision as well. I also talked last week that eye movements actually cut your conscious experience before and after that. So if you, the best way to see this experiment is that not to move your eyes at the center. And then that gives you the best visibility. And that's what subjects do in general. Okay, and therefore this expectation and memory was already minimized or ruled out from this experiment. And then key result of that this experiment was that with respect to the color that was presented at the center, and then another central patch, so basically this is a center kind of situation. Then the diagonal pair, which means that when you present this light blue and then you also present the light blue, then people tend to say that, oh, this is similar. This is a color axis is a similarity and the 0 is a most similar. And then when it's presented with a purple and the green, that's most dissimilar, right? And then this is the case for also periphery to periphery. That's this quadrant. And also periphery to central is also the same kind of color relationship. That's a critical thing. So this means that what we see at the fovea, near fovea, and what we see in the periphery is giving more or less the same kind of color structure and the relationship. Okay. And then, but here there's a twist in the experiment. So I need to give you a little bit more detail from the last week. But before going further, I just wanted to give you a quiz. Can you, okay, maybe do the poll here, launch, okay. So I set out a poll, option A. So what I'm gonna ask you is to put your thumbnail, at your arm's length like this, extend your arm's, thumb at the arm's length, and then look at your thumb. And then the question is whether, wait a sec. Yeah. You don't see that display. Wait a sec. Do you see my screen?
Yeah.
Okay, so then that's just my end. Okay, so just coming back to this. So if you present put your thumb in front of you, and then what's the sort of the width of your thumb? That's the question. And so do you still see the quiz or poll option? And
Yeah.
option A would be let's say 10 degree, and then option B is 1 degree, and then option C is 0.1 degree. What's the width of the thumbnail? At your arm's length. If you're not sure, just choose by hunch. Okay. Or the correct answer is actually this one, 1 degree. So that means that at your arm's length, if you have 360 of them, then it goes one round from the front of your fixation to the back, and then coming back to here. 360 of them, roughly 1 degree. But in fact, it's 1.4 or something like that. Okay, so this is quite useful and also important kind of number figure, so you should remember. And then with that, what I wanted to show is this. So here is what our experiment basically did. Here you see that if you can adjust your distance to the display, like in my case, it's roughly this distance from my relatively big display. And then 1 degree distance from the fixation is roughly this circle. And then 10 degree from the fixation is roughly this circle to the left. Probably if you adjust the distance like this, the color of the most peripheral stimulus is not that visible, right? I think. However, if you make the stimulus appropriately big, like this, then I think it's quite obvious that so fixate at this in the center, at the cross, and then can you see the color of the right side and the left side clearly? Maybe you can say in a chat box yes or no. Okay, that's pretty obvious. I hope. And then also here, let's go from the top. Would you agree on this top row? When you're fixating at the center here, do you see the color on the right and left clearly? If it's not sure, then no, maybe or something is fine as well. Okay. But then maybe if you try this one, the middle one, what's your experience? Okay. And then the last one, yeah, okay. The last one, when you see this, what do you feel? Can you compare the color between the right and the left? Okay. All right, so hopefully, hard to tell, yes. So because this is, exactly hard to tell, because we don't present this in a controlled experimental, situation, right? But if we present this just briefly, and then you rate, similarity of these things, across the trials, then you can tell that to the experimenter. And then as a result, we can have a phenomenological report from the subject, and then we can make a more clear and also confident kind of statement about this. And then what we found is this type of the result. So here's the previous presentation where we've had the central and also peripheral stimuli generated basically the same kind of structure. And here the stimulus was magnified. So small one at the fovea and then magnified at the periphery. And that's the one that we saw in the sort of the third level of the demonstration. Actually, the fourth one. So even though you said that it was hard to tell, if you are subjected to this experiment, you can do this. Yeah, so that as Dante said that the pre-existing knowledge basically always hinders you to be certain or uncertain about your color stimulus. But under this experimental situation, at each trial, the location of the stimulus is uncertain, unpredictable, and also exactly what color will be shown is also unpredictable. And therefore, you can't rely on your memory and you can't rely on the expectation. and then just report this in similarity. Does it make sense now? And under this situation, if you present the stimulus that looks like, that looks like the bottom one, the 0.1 degree diameter and 0.45 degree diameter on the left, then you can report something like on the left side. But if both of them are very, very small, just like a tiny dot on each case, then what happens is something like this. You still see a pattern within the periphery comparison here, like, these shades of the yellow to green here seems to be similar to each other compared to the shades of the blue to red or blue to purple here. That seems to be different. So if you present very, very tiny stimulus, which is not magnified for the periphery, then these two stimulus, these two tiny dots pair looks almost like similar here. But if you present both of them at the center, near center, then it's totally discriminable. And also the pattern of the similarity looks almost the same here, although these two are coming from completely different subjects. Okay, so the point here is that when the stimulus is in the same size here, so the important thing is here at the top. When the peripheral stimulus becomes slightly bigger, like the third one in the last demonstration, then you can see it almost really clearly across peripheral and central. But when the peripheral stimulus remains very tiny and then move it to the periphery, then you start to lose color sensation. And many previous philosophers and scientists, psychologists sometimes mix all these things together, and then just paying attention to this fact, without magnifying the stimulus to put it in the periphery, we start to become blurry in color sensation, and that's what they mean by loss of color experience. But that's not the same as you can't see the color at the periphery. Okay, I hope this is clear. So, but so far, does it make sense? Is there any question? If you have any question, you can ask either chat or ask in speaking. Either way is fine. Okay. All right, then move on. So why does our size matter? That's the next question. And here comes this important concept of the receptive field. So the here is the first demonstration of the receptive field concept. But okay, now it's been 25 minutes, so I'll take a break here, and we'll come back in 5 minutes. Okay.